Okay, so hello everyone. Thanks Maggie for the introduction. My name is Pablo Gimeno from the University of Zaragoza. Now we're going to change topic. We're going to move towards multiclass audio segmentation, which is also related to the topic we are discussing here in our explainable modernization group. What I'm going to tell today is part of my PhD thesis, like just a few selected topics of things that I discuss more in detail in my PhD thesis. So if you have any further question or any further ideas, you can also have a look at my thesis. So the outline for the presentation, I will first provide a brief introduction on what is audio segmentation and why it's important and the context on it. And I will then dive in directly to the two main blocks that I'm going to be discussing. The first one, it's some experiments we reported on the use of recurrent neural networks for multiclass audio segmentation. And it's really convenient that Victoria here explained most of the AUC optimization techniques, because for the second block of this presentation, I'm going to be also talking about this kind of optimization techniques, but in the context of audio segmentation. And in addition to this, we'll be trying to expand this to the multiclass classification framework for this audio segmentation task. As I said, this is just two chapters of part of what I did in my PhD thesis, recently defended in last May. So a little bit of context about the full environment. As you probably know, multimedia data is huge online. Just some data here. For example, YouTube has around 82 years of video content uploaded every hour. And if we have a look at Spotify, for example, we know that we have about 433 million monthly active users that can listen up to 82 million songs. So data is here and it's huge. And what multimedia providers want to do with this data is to provide value to the clients by somehow being able to analyze and catalog that content. With this huge amount of data, it's clear that manual annotation is out of the way. It's not feasible. So, because of course it's expensive and time-consuming. Here I'm just providing an example. Transcribing a file can take up to 4 to 6 times of the original length of the file. This is the main motivation for part of the work I've done in my thesis and what I'm going to talk today, which is the need for automatic systems that can analyze, index, and retrieve information from multimedia streams. Particularly, we're going to be focusing on audio streams, but this could also apply to any other multimedia stream that you can think of. And in this context, I'm introducing to you the audio segmentation task, which tries to divide an audio signal into smaller fragments according to a predefined set of attributes. Here you can see, oops, sorry. Here you can see an example of an audio signal with 3 different annotations for 3 different classes, A, B, and C. This is just a imaginary audio segmentation system with 3 different classes that will be related to some attributes that we want to find in this signal. So this audio segmentation is it's basically a support technology that can allow the accurate application of other information retrieval systems. Probably you've heard of speech activity detection, which is a main pre-processing block in ASR, for example. Or if we want to use audio enhancement, it would be nice to have an intuition on what is the most noisy samples on this audio signal. So last, I want to talk about the multi-class paradigm. Here, and well, in all my PhD thesis, I've been working mainly on the multi-class approach, which supports only one class active at a given time. But for example, in our work in the explainable modernization team, we are focusing on the multi-label approach, where more than one class can be active at a given time. But for this talk, you can always think that we are doing multi-class, so we can only have one active class at a time. So this was just a brief introduction and motivation to the topic. I will now jump into the first main block, which is going to be about recurrent neural networks for multiclass audio segmentation in broadcast domain data. Basically, my thesis has been focusing on broadcast data, and for this talk, I'm going to be talking mainly on broadcast domain. So, as you probably heard of several well-known binary segmentation tasks, speech activity detection. There is also others, such as music detection, the equivalent in music, or other binary tasks that try to separate speech and music, for example. In these experiments, we are going to be dealing with a different audio segmentation task that's been designed from a multi-class perspective. Mainly, we are going to be trying to separate speech, music, noise, or a combination of these classes. In these particular experiments, we are going to be exploring the use of different RNN architectures in different variants for this task. Furthermore, one of our main contributions is the introduction of temporal pooling mechanism in order to remove redundant information in the temporal axis. This allows to improve the performance of the system and additionally reduce the number of operations per second. So just an introduction to I'm going to be brief in some of the details, but if you have questions, please ask, because I need to go fast on some of the exact details. For the RNN classifier, here we propose the use of what we call combination and pooling blocks here in between different bidirectional LSTM layers, which are described here in the next slide. We tested in 3 different variants, one that's using only the time pooling, and one that incorporates also a convolutional layer in order to mix the channel information, and the one that only uses the convolutional layer. So you have to trust me here that the one that performs the best is the time pooling. I don't have time to provide all the experiments to demonstrate this, but we showed in the original paper that applying time pooling in between the 2 bidirectional LSTM layer provides a boost in performance, while at the same time it reduces significantly the processing time of the neural network. In addition to this, in order to provide an additional inertia on the labels, we are using a post-processing module implemented as an HMM resegmentation. What we do here is that we model each one of the classes in the system as a state in the Markov chain, and we just apply this other 2 mechanism to enforce a minimum duration of the label in the inference. One of them is the RNN score downsampling using an L-order averaging filters, and we use a left-to-right topology with a number of tight states for each one of the states. This way, we have this equation that enforces a minimum duration of the length in the inference time. So let me talk a little bit about the data, how we are dealing with the data. I want to introduce the Albaicin 2010 audio segmentation task, which tries to separate 5 different classes. Here we are dealing with speech, music, speech and music, speech and noise, and 5th class that we call others, which is basically silence and everything that's not been described in the previous classes. As you can see, it's a multi-class approach because we don't have like several labels active at the same time, but we model that into different classes. This audio is coming from broadcast news domain, and we have around 87 hours of training and 29 hours of test. I won't go into details in the evaluation metrics, like we use segmentation error rate, which is basically inspired on the diarization error rate. And for the original evaluation, in order to be comparable with the original evaluation, we use the average class error. Okay, I'm going to be presenting only a subset of the results we have. I want to focus first on the feature analysis. We use a different set of features in order to train our systems. We saw that including, in addition to traditional log-mel coefficients, we included chroma features in order to improve the musical information in the system. And we saw that including this and the first and second order derivative, we saw significant improvements mainly in the classes that contain, in the classes that contain a music, like music and the speech and music class. The next part I want to talk about is the actual introduction of the pooling mechanism. Here I'm showing the in-depth analysis for the best performing architecture. That is the one using a time pooling in between the first and second bidirectional LSTM layers. We did an analysis using both average and max pooling, and as you can see, while the max pooling quickly degrades when using large pooling factors, we have a more or less stable performance using the average pooling. And the good thing about these results is that we have less operation per second, and we have around a 5% relative improvement compared to not using it in our architecture. So as a side part of this, we wanted to remain comparable with the original evaluation. So we couldn't add any external data sources to the experimental setup, but we wanted to somehow use augmentation. What we came up with is using this mix-up augmentation. Mix-up is a data agnostic routine that can generate virtual examples through linear interpolation. So basically what we do is we get two different examples and we linear combine them using this weights sample from a beta distribution, where we have this alpha mix-up hyperparameter that controls the strength of this interpolation. By doing this, we could get another 5% overall relative improvement without adding any external data in the augmentation process. Which is also interesting is that the best improvement is obtained for the speech and music class, which is the class that is a pure combination of other classes in the set, the music and speech classes. And finally, I want to talk a little bit about the HMM resegmentation, the post-processing module. Here I'm showing the relative improvement observed with applying this. We see that for different hyperparameters, using different lengths, different length order in the filter, and for different number of tidal states, we have like a relative stability region here around 0.5 to 1.5 minimum segment length, and this performance decreases faster when we start to increase this minimum segment length. Okay, so this was the first part about the RNN.
Quick question.
Yeah.
First, in your data set, I was thinking about your classes. You have speech, you have music, you have noise, and you have other, right? And I guess you're dealing with, was this broadcast data? What was?
Yes, it's broadcast.
So are there segments where there is only singing without background music? And if so, what class would you give it?
Only singing.
Only vocal singing with no instrumentation. Is that music or speech in your classifier?
I would say that's music.
So okay, and secondly, do you know how performance on that is? Is it better or worse than speech, or are there enough examples in your test? Do you know?
To be honest, I don't know.
Okay, all right.
But it's a broadcast news, so you would expect like the typical jingle in news or like music. Music is not really common in the data set. It's just it's less than 10% in the data. So it's not like really the most common class.
Okay.
And like the typical example of music here would be like a jingle, like at the start of the broadcast news or whatever. Like it's not. You wouldn't expect to have.
It's not a music radio station with songs.
No. It's a TV news show.
All right. Okay. Thanks.
Okay, so for this second part, it's very convenient that Victoria just explained most of it. So I'm going to go directly into what I added on top of the AUC optimization techniques, which is the generalization of these methods in order to be applied to multi-class classification. So as Victoria has explained, AUC optimization has some capabilities on several, not only audio segmentation, but several audio processing tasks in general. But due to its intrinsic nature, it's limited to be applied on binary tasks, because it's how AUC works. It's usually applied in binary evaluation problems. Furthermore, we have several multi-class segmentation tasks that pose new challenges, and we have increasing possible error. We have several classes that can be confused. Like in general, multi-class segmentation is harder than binary segmentation. And in addition to this, data scarcity is even more relevant because it's harder to annotate a data set with several classes with complex taxonomies. So we came up with the idea of trying to generalize these AUC optimization techniques that has been applied mostly on binary segmentation tasks in order to be able to use them with an arbitrary number of classes, in order to use them in any multi-class classification framework. So some precedents here. Before this multi-class application framework, we've seen several AUC optimization techniques being applied in binary segmentation tasks. For example, speech activity detection, or we had some work on music detection for using AUC and partial AUC techniques. We saw that this was especially useful in limited data scenarios, and we also demonstrated that this has showed a significant improvement compared to traditional cross-entropy training. I have some, this is from our paper in partial AUC. In addition to using AUC techniques, we included, we went beyond the AUC and we tried to use partial AUC and other loss functions that are based on AUC and partial AUC. I won't go into the details because I want to focus on the multi-class part, but just some results from this paper that also show that here in red you can see the red line is the cross-entropy training, and the other three lines are AUC-based training strategies. So you can see that for binary segmentation task, AUC works, and it works better than traditional cross-entropy training, in this, especially in these cases with where we have little data in order to train. So, well, just a brief reminder. Victoria explained it very well, but just a brief reminder of what we do with AUC optimization. As we cannot directly optimize the AUC expression, we are going to be using the sigmoid approximation in order to obtain a differentiable loss function. So, and the question now is, how can we go from a binary AUC to a multi-class AUC optimization? So we need to first refer to the multi-class definition of AUC in the literature. So there's been usually two main approaches to this, and both of them are based on are computed by averaging binary AUCs. The first one of them is the 1 versus 1 approach, which is shown here. I'm showing here a graph with the idea where a pairwise combination of classes are used, and here we will get the blue with the orange, the blue with the red, and the red with the orange, all the possible pairwise combination of classes, and for each one of them we will use as target and non-target, and we will compute a binary AUC. Finally, all of them will be averaged, and that will be our multi-class AUC metric. The other approach is the 1 versus rest, which is based on a binarization solution, where we get one of the classes as target and the other classes as used and non-target. And we basically do the same. We compute one binary AUC for each one of them, and then we average all the values to get the multi-class metric. So if we know how to optimize binary AUCs, and we know that multi-class AUC can be computed as binary AUCs, then if we just plug in the sigmoid approximation and apply it a number of times on this multi-class AUC definition, we can define this differentiable multi-class loss function. We can do it for both versions, for the OBO and the OBR versions of this multi-class AUC. Just some comments on the experimental setup here for this part. We are keeping a simple neural network setup with 2 layers bidirectional RNN, and we use the same set of features as in the previous experiment with a MEL filter bank, log MEL filter bank, and chroma as input. For the data here, we are using a different one. We're using a task proposed in the OpenVMAT dataset, which try to separate foreground music, background music, and no music. I'm moving now to the results. Here we are comparing our two AUC proposal with a traditional softmax cross-entropy training and an angular softmax. And what you can see is that basically the AUC optimization techniques provide a better performance when compared to the AUC, when compared to the softmax training, both the angular and the traditional softmax. And in addition to this, the OVO approach seems to be better than the OVR approach in all cases. And finally, some per class results. Here I'm showing like the different performance for different classes. In general terms, same trends apply here. Like we see that the OVO approach is better than the OVR in all cases. And we see some boosts in performance for specifically for the background music class, which is the hardest class to classify. And it's also the most ambiguous class. Like sometimes it's hard to say what this is background, this is foreground. And for this class, it's for the class that we see like the best improvement when compared to traditional cross-entropy training. So that's it. If you have any questions, I'll be happy to take them. This is just, as I said, this is just 2 chapters of my PhD thesis. It's online, so if you want to have a look, it's there, and it's more detail and with more experiment than what I explained here.
Any questions? I have one regarding the chroma features, because the chroma features are supposed to be related to the octavation. So is it relevant for any kind of music? So for example, if you have some very melodic music, so I think chroma is very interesting.
Yes, that's the main use case for chroma, I guess, like for melodic music. Maybe for something that's not melodic, it wouldn't be as good, probably.
Okay, so for jingles, it could be nice.
Yes.
Okay.
But if you have something more percussive, probably it's not the best approach.
Okay.
Yeah. So I have a question about the most confused classes in.
I had one slide with the confusion matrix, but I had to remove it in the end. So, yeah. Usually, in the first part, in the multiclass segmentation with the Albaicin, the most confused class was a speech that was a speech with music that was mostly confused as a speech with noise, and the other way around, like mostly a speech with noise that was confused with a speech with music. I think that it somehow makes sense that music and noise can be at some point get to be confused. Like if music, like it's very in the background, can get to be confused with noise. As noise is really wide in terms of definition. Like music is like everyone has like a general idea of what is music, but noise is like a more diffuse definition. So that can get to be confused at some point. But for example, in the experiments with Albaicin, music was like the best class, like with the best performance.
Yeah, so then what do you put in the others class? I'm curious to know what are the others.
Everything that's not defined in the other classes, like silence, for example, is there. Like if you have like pure noise, would be there. Like if you have a speech with music, a speech with noise and music, and everything that's not in these 4 classes is there. So you have, for example, only noise, it would be there.
Excuse me, Pablo. I think I have a little bit salty question. So, at some point, I wanted to actually use one of those models for like mainly semi-supervised learning and everything. and I couldn't find any online. Like, it's pretty surprising. Is it like a community practice? Is it like the data sets for training are supposed to be proprietary or something? Like, generally, if you go on Hugging Face, you basically find models for everything. But if you want a model for this kind of things, I find one that is pretty much undocumented. I mean, it's weird. Do you have an explanation?
Well, I can only talk from my side, and it's true that none of my models are online. That part you're right. I think, to be honest, I think I've never seen any of these kind of models online. I can only talk on myself, like, but that's a nice question. Like, probably the one who was working at the explainable realization team, it will probably be online at some point. So maybe once we are done with that, you can try it if you want.
If I could just make a comment, because I think it's because supervisors are not pushing enough the students, and there are some in the room that have been pushed, but obviously not enough. So I think the community still need to push that.
So, Pablo, I had a question which is not specific to what you did, but more generally, when you have these multi-class problems, I don't know what to make of averaging the areas under the curve. I'll tell you what I mean by that. If I have a binary classification problem, I know how to interpret the area under the curve, right? Because the curve corresponds to various operating points by sweeping some threshold. And you're simply saying, averaged over all operating points, what's your performance, right? That's the AUC. Now, if I do this pairwise thing, then for any one class, when it is compared with another class, the point at which you get a certain false alarm and misses is some threshold. But when you compare that same class with some other class, to obtain that false positive, false negative thing, you get a different threshold. So in what sense is this average meaningful? Because I don't know what to make of it, because is it some kind of average of all operating points? I don't think so, because each operating point is a different point on each of the AUCs, each of the curves. So what are you averaging actually?
I think it serves only like a overall measure of performance, like for all the classes in your dataset. Like, of course, if you want to have an intuition of each one of the classes, that's mainly what I use two different kind of metrics in my evaluation. Like, I use obviously the AUC, the multi-class AUC, and then I had to use another, like this course for the precision and recall, because if I want to know what's happening in each one of the classes, that's the only way to know it. Like, but yeah, it's a good question. Like, I guess that my intuition is that you can only use this multi-class AUC like an overall measure for all the classes in your set. But yeah, as you said, like, if you select different pairs of classes, like, of course, your threshold will be completely different depending on how your classes are selected, and it's hard to get an intuition on this on each one of the multi-class approaches. Yeah.
Okay. All right. Yeah. I don't know whether there's a good way to interpret it. That's all. I mean, because, like I said, I can interpret binary by saying, randomly pick a threshold, do it many, many times, and you'll get some kind of average which is reflected by the area. So if we carried out the same simulation with this system and said randomly pick many operating points, I don't even know what it means to pick an operating point, because each pair has a different choice to be made, and and the system itself makes its own choices. Of course, it has its own way of doing multi-class. So I don't know if there's a way to relate the operating points of the multi-class system with all the pairwise. I mean, I don't know, somebody should think about it.
Well, technically, you could choose a set of threshold and apply it to all the pairwise combination of classes, and you could get more or less the same intuition on the AUC. But even though it's hard to relate, like.
But that's not how the system functions, right? The system doesn't do pairwise things. It just gives you one of a multi-class label.
Yes, yeah, of course. Like when you do inference, you only get one of the values. Yeah.
Right.
Yeah.
So in that case, what is the threshold we are sweeping, and how are we getting these different?
In this multi-class approach, what I usually do is just get you apply the softmax in the end, and you get the Rmax of the softmax value to get the predicted class.
Okay. Right. Anyway, we'll talk more. I don't have a good intuition for it. That's all.